Hello guys, how are you today? So today I will be explaining the chemistry AMS of term 2 week 6. Usually my friend explains it, and thank you so much for her explaining. But this week I will be explaining it instead of her. Now, very simply, anything that corresponds to a noble gas means that it has what? 8 valence electrons. So when doing the electron configuration, we're going to put 1, 2, 3, 4. Okay, here maximum 2, maximum 8, and maximum 2. So if it has 8 valence electrons, that means the last shell or the last bar is supposed to have a number of 8. So 2, 8 is an option, or 288 is also an option, but 2882 is not an option. For it to be a noble gas, it must have 8 valence electrons. So this is an option, and this is also an option. Moving on to question number 2. We are given the mass in grams, okay? We are given the volume. We are given the temperature in degrees Celsius, so we change it to Kelvin by adding 273, which gives us 300. We have 2 atmosphere. This is our pressure. They need us to find the molecular mass. Very simply, we know PV is equal to nRT, and N is equal to what? The mass over molar mass. So to find the value of the molar mass, we are just gonna make the number of moles the subject of this equation. So then it becomes N is equal to PV over RT. So the number of moles is equal to PV. What is PV? PV is 0.8 times 2 over RT, which is 300 times 0.08. So if you do it on your calculator, you will get an answer of, I will write it as a fraction, 1 over 15. Okay, so now the number of moles is 1 over 15. And we also know that number of moles is mass over molar mass. Our given mass is 3.73, and we are looking for the molar mass. So we can apply cross multiplication, and we get that molar mass is 15 times 3.73, okay, which is approximately 55.95. If you round it, it is then 56. So the molar mass is 56 grams. Moving on to question number 3. The empirical formula of a compound X is CH2O. Okay, we are given what? The empirical formula. If the molar mass of the compound is 60 grams per mole, what is the molecular formula? Very simply, when we face something like this, we are gonna take the given molar mass, which is 60 grams per mole, and we are gonna divide it by the molar mass of the empirical formula. So what is the molar mass of this? It's gonna be 12 plus 2 plus 16, which is 30. So 60 divided by 30 is equal to 2. So that means we are gonna take this one, CH2O, and we are gonna multiply it by 2. So it becomes C2H4O2. So C2H4O2. Moving on to question number 4. This question is a nice question. A student wants to find the maximum mass of aluminium oxide, Al2O3, produced on a sample of 0.8 moles of aluminium. So aluminium was 4, and then it became 0.8 moles. They need us to calculate what? The maximum mass of aluminium oxide. So 4 became 0.8. How much will 2 become? We'll apply cross multiplication. So it becomes 2 times 0.8 divided by 4. 2 times 0.8 divided by 4 gives us an answer of 0.4. But this is what? The number of moles. We're not looking for the number of moles. We are looking for the mass. So what we're going to do is we are going to take our mass, which is Al2O3, and we are going to multiply it by the number of moles. So what is the mass of Al2O3? It is 27 times 2 plus 16 times 3. So 0.4 times 27 times 2 plus 16 times 3 will then give us an answer of 40.8. So our answer over here is 40.8. Moving on to question number 5. This question is a very nice question. A hydrocarbon HC, for example, HXCX, okay? Or it could be CH, so CXHY. Alright, it's more preferable to put the C first. Is 75% carbon by mass. Find its empirical or simplest formula. Now hydrocarbon, let us assume it is CXHY, is 75% carbon by mass. So let us write it as an equation. 75% plus 25% is equal to 100%. So if we took the total mass to be 100 grams, okay, that means 25 is hydrogen and 75 is carbon. Now let us find the number of moles. To find the number of moles, we divide by the molar mass. Okay, and we are given 75 divided by 12, which is 6.25. And then 25 divided by 1 is 25. Now, what we are gonna do is we are gonna divide by the smallest number. Okay, so in this case, the smallest number is 6.25, and we will get an answer of 1. And then 25 divided by 6.25 is 4. So that means the carbon has 1 atom, so C1, or we do not put the 1, so it's gonna be C. And the hydrogen has 4 atoms, so H4, and we are only gonna put 4. So the empirical formula is CH4. Moving on to question number 6. Here they're asking for the theoretical yield in tons. Very simply, we have when 0.5 tons of H2 gas reacts completely with CO gas, the amount of methanol produced was 3 tons. Very simply, 3 tons is what? Is our actual yield. Okay? Now they need us to calculate the theoretical yield. First thing, before we move on from the actual yield, to calculate the theoretical yield, we are going to take the given mass, which is 0.5 tons, or in other terms, 0.5 times 10 to the power of 6 grams. Okay? Then we are going to find the number of moles of what? Of the 2H2. How much it became. So we are going to divide it by the molar mass of H2, which is 2. And we are going to get 0.5 times 10 to the 6 divided by 2. We are going to get 250,000. Now, 2 moles became 250,000 moles. What about 1 mole? Definitely by applying the cross multiplication, we are gonna get 250,000 divided by 2, which means that 1 mole will become 125,000 moles. Now the theoretical yield is the number of moles multiplied by what? By the molar mass of CH3OH, so 12 plus 3 plus 16 plus 1. So we get an answer of 4 million. Okay, and then if we divide it by 10 to the power of 6, we will get 4.0 tons. So our theoretical yield is what? It is 4.0 tons. Now to find the percentage yield, you should know that percentage yield is actual yield, which is 3.0 tons, over theoretical yield, which is 4.0 tons, times 100. So 3 over 4 times 100, you will get an answer of 75. So it is 75% of percentage yield. Please pay attention to the significant figures as well. Now write the electron configuration of a boron atom. I think this is a mistake over here, because on the periodic table, the boron atom has 5 as its atomic number. So based on the SP rules, we're gonna start, first of all, 1s to the power of 2. Actually, if you don't wanna do it like this, let us do 1s, then s, then p, then s, then p, then d, then s, then p, then d, then f. Okay, we will stop here for now. So this becomes 1, 2, 3, 4. Okay, now this one we start at 2, so 2, 3, 4. This one, we start at 3, so 3, 4, and this one is only at 4. Now S is always to the power of 2. That means 2 electrons fit in S. And P is always to the power of 6. That means 6 electrons can fit in P. D is maximum to the power of 10. And F, I kind of forgot, so I'm just gonna leave it blank for now because it's not important. Okay, so let us fill in starting with 1s2. So 1s to the power of 2. This is 2 electrons gone. So 5 minus 2, we are left with 3 electrons. So again, we will put 2s to the power of 2. We put 2 electrons again. So that is 3 minus 2, which leaves us with 1 electron. So we move on to what? To 2p, but instead of putting it to the power of 6, we put it to the power of the number of electrons left, which is 1. And if you add 2 plus 2 plus 1, you will get a total number of 5. So remember, 1s, and then you put it to the power of 2, because s is always to the power of 2. That means 2 electrons are gone. Then you move on, 2s to the power of 2. 2 electrons are gone. Then 3s to the power of, not 3s, my apologies, 2p to the power of 1. And like that, you would have finished the electron configuration of the boron atom. Moving on to question number 8. Consider the following chemical equation. We are given 1 mole of H2 will react to the 0.25 moles of O2 to produce H2O. Which reactant is in excess? Thankfully, they made it easy for us and they gave us the number of moles. So what we are going to do is we're going to take the number of moles and divide it by the coefficient. So for H2, it is 1 over 2, which is 0.5. For O2, it is what? It is 0.25 over 1, which is 0.25. Now, which one is less? 0.25 is less. That means H2 is in excess. So which one is in excess? It definitely is H2. Pay attention in the exam if they ask you which one is in excess and which one is limiting. Now here, this is a really important one. They told us to write the electronic configuration of the oxide ion. They told us oxygen has an atomic number of 8. Atomic number of 8 means, let us do the thing. It has 2 over here and 6 over here. That means it's not a noble gas since it did not have the noble gas configuration of 8 valence electrons. So to make it into a noble gas or a stable ion, that's why we have ions, they added 2 electrons to the last. So instead of 6, it became 8, and now it has the noble gas configuration. So if we are going to write it electronic configuration, we are going to be using the S. So it is going to be 1, or let's start S, then SP, then SPD, then SPDF, then 1, 2, 3, 4, 2, 3, 4, 3, 4, 4. Okay, we need to fill in what? We need to fill in 2 and then 6, but because there is 2 minus, we are gonna be adding 2 electrons to the valence electrons, which is 8. So in total, we need to be filling 8 electrons. So we start 1s to the power of 2, that is 10 minus 2, we are left with 8. Then 2s to the power of 2, 8 minus 2, we are left with 6. Then 2p to the power of 6, 6 minus 6, we are left with 0. We wrote the electronic configuration of the oxide ion. So it is 1s to the power of 2, 2s to the power of 2, and then 2p to the power of 6. Moving on to question number 10. Again, we need to write the electronic configuration of the sodium ion. So S, Sp, SPD, SPDF. Then we have 1, 2, 3, 4, 2, 3, 4, 3, 4, 4. we need to fill what? Pay attention. They told us sodium has an atomic number of 11. So if we do the configuration, it is 2, 8, and 1. But they need of a sodium ion. But here's the thing. Sodium, is it easier for it to gain 7 electrons so it has the configuration of 8 valence electrons? Or is it easier just to lose 1 electron and then it has the electric configuration of a noble gas? Very simply, it's easier for it to lose 1 electron. So that is why it is gonna be only 8. We are gonna be working for only 8. So please pay attention if they ask for the sodium ion or for the sodium atom. This word is very important. Okay, so we are gonna start. We start 1s to the power of 2. So it was 10 minus 2. We are left with 8. Then 2s to the power of 2. 8 minus 2, 6. Then 2p to the power of 6. 6 minus 6 is 0. So it is 1s to the power of 2. 2s to the power of 2, and then 2p to the power of 6. Moving on to question number 11. Here, pay attention. They did not say anything about a sodium ion, so we are working with a sodium atom. That means it is 2, 8, 1. In total, it is 11. So if we are gonna do the S, SP, SPD, and then SPDF, then we have 1, 2, 3, 4, 2, 3, 4, 3, 4, and then 4. Okay, so first thing we are gonna start with is 1. 1s to the power of 2. 11 minus 2, 9. Okay, then 2s to the power of 2. 9 minus 2, 7. Then we have 2p to the power of 6. It is 7 minus 6, which is 1. But do we move on to 2D? No. We move on to 3s based on this order. So 1s finished, then 2s, 2p, then 3s, so 3s to the power of 2. But since we only need 1 electron, we will actually put it to the power of 1. So it's gonna be 1s to the power of 2, 2s to the power of 2, 2p to the power of 6, and then 3s to the power of 1. Now, can we figure out to which group it belongs? Definitely by the number of valence electrons, which is 1. So it belongs to group 1. And to which period does it belong? Just look at the number next to the last one. Since there is a 3 next to it, then it belongs to period number 3. Moving on to question number 12. They said this is the electronic configuration of carbon, 2, 4. They said fill in the blanks for the correct number of valence electrons of carbon. Very simply, valence electrons is the last number of electrons. In this case, it is 4 valence electrons. Moving on to question number 13. A sample of a compound contained 0.96 moles of hydrogen, 0.24 moles of carbon, and 0.48 moles of oxygen. So 0.96, 0.24, and 0.48. How I do it personally is I add them all. So 0.96 plus 0.24 plus 0.48, we will get an answer of 1.68. Okay? Now what am I gonna do? I'm gonna take hydrogen by itself. I will take the number of moles of hydrogen divided by the total. Okay? And I am gonna get 0.96 divided by 1.68. I'm gonna get 4/7. For carbon, let us do the same. So for carbon, it is 0.24. So it is 1/7. And finally, for oxygen, it is 0.48. So it is 2/7. So again, what did I do? I added them all. I took the total. Then I took the mole of each one, divided it by the total. So 0.96 divided by 1.68, 4/7. Then 0.24 divided by 1.68, 1/7. Then 0.48 divided by 2/7, divided by 1.68 is 2/7. Now what we are going to do, we have C, which is 1/7, H, 4/7. This is a 4, hold on. 4/7, and then O 2/7. Since all of them are over 7, we can just multiply it by 7, okay? And we are gonna get what? CH4O2. So very simply, the simplest formula is CH4O2. So it is C nothing, H4O2. Moving on to question number 14. Oxygen has an atomic number of 8. They need the correct electronic configuration. It is 2, 6. So remember, maximum 2, maximum 8, maximum 8, and maximum 2. So it has an atomic number of 8, so it's gonna be 2. Then 8 minus 2, we are left with 6. We put it over here. Moving on to question number 15. Now, for this question, if we take 60 milliliter of solution, remember the solution should always be in liter, but in this case, you are gonna see why we will not change the unit. Out of a 0.40 concentration, so this is what? This is our volume, this is our concentration, so we'll say volume 1, concentration 1. Okay, they added it to 140 milliliters of distilled water. Now this is not our volume 2. Why? Because this one has a volume of 60. You added it to 140 milliliters to give you 200 milliliters. This is what? This is our volume 2. They need, what will the concentration of the solution become? Very simply, the equation is C1V1 is equal to C2V2. This is something from last year. So C1 is 0.4 times V1, which is 60. Now, why do we not change the units? I will keep the units now just to show you why we do not change it. Times 60 milliliters divided by volume 2, which is 200 milliliters. Milliliter and milliliter will cancel out, and what will remain is the unit of this, which is molarity. And if you do it on the calculator, 0.4 times 60 divided by 200, we will get an answer of 0.12 molarity. Again, I will repeat, I feel this is an important concept. This is what? Our first volume. This over here is our first concentration, but 140 milliliter, you added to it 60 milliliter, so it becomes 200 milliliter. This is volume 2. Equation is C1V1 is equal to C2V2. Okay, so it's 0.4 times 60 divided, or let's not say divided, is equal to C2 times 200. So then C2 is equal to 0.4 times 60 divided by 200, which is then 0.12. Okay? Moving on to question number 16. This is a nice question. Okay? How many grams of CaO are produced if a sample of 20 grams of CaCO3, 20 grams of CaCO3 means 20 divided by the molar mass of CaCO3, which is 40 plus 12 plus 16 times 3. So on the calculator, 20 divided by 40 plus 12 plus 16 times 3 will give us 0.2 moles. Now they need the grams of CaO produced. So 1 mole of CaCO3 gives us 0.2 mole. Then 1 mole of CaO will also give us 0.2 moles. But do they need the number of moles? No, they need the grams. So 0.2 times the molar mass of CaO, which is 40 plus 16. So 0.2 times 40 plus 16 will give us an answer of 11.2. So the grams is 11.2. Now they need the volume of CO2 produced. Again, we said 1 mole of CaCO3 will give us 0.2 mole. So 1 mole of CO2 will give us 0.2 mole. We multiply it by STP, which is 22.4. So 0.2 times 22.4. We will get an answer of 4.48. So our answer over here is 4.48 liters. Moving on to question number 17. Okay, so what mass of Fe2O3 must react to produce 90.5 kilojoules? This doesn't mean anything. This just means that it is plus 181 kilojoules, 18.1 kilojoules over there. So what mass must react to produce 90.5? Very simply, you take the given energy divided by the original energy, and you are gonna get how much? 90.5 divided by 18.1. You are gonna get an answer of 5. So what mass of Fe2O3 must react to produce? Definitely you are gonna multiply everything by 5. So times 5 times 5 times 5 times 5 and times 5. Okay? So it's gonna be 5 moles of Fe2O3. To find the mass of 5 moles of Fe2O3, we are gonna multiply it by the molar mass of Fe2O3, which is 160. So 5 times 160 will give us an answer of 800. Now pay attention, they said 3 significant figures. 800 is only one significant figure, but if you put 800 dot, then it will consider it correct to 3 significant figures. Now, they said what volume of CO2 is produced at RTP when 90.5 kilojoules are released. So we multiplied everything by 5. That means it is now 15 moles of CO2 multiplied by RTP, which is 24. So 15 times 24 will give us an answer of 360. But to 3 significant figures, this is only 2. So we put a dot. So it is then 800 dot grams and then 360 dot decimeter cube. Number 18, how many moles of KCl are required to produce 14.2 grams of Cl2? Very simply, 14.2 divided by the molar mass of Cl2, which is 35.5 times 2. So 14.2 divided by 35.5 times 2 will give us an answer of 0.2. Now, this became 0.2. How many moles will the KCl become? Very simply, 1 gave us 0.2 moles. So 2 is gonna give us 0.4 moles, but to 3 significant figures, so 0, 0. Here we do not put a full stop because it is after the decimal place. So the number of moles is 0.400 mole. Alright? How many grams of Cl2 are produced from 0.300 mole of F2? So 1 mole of F2 became 0.3 moles. So 1 mole of Cl2 is also gonna become 0.3 mole. Okay, so we are gonna take 0.3 and multiply it by the molar mass of Cl2, which is 35.5 times 2. So 0.3 times 35.5 times 2. This will give us an answer of 21.3. So our answer is then 21.3 gram. Okay? Moving on to question number 19 and the last and final question. A sample of 5.5 grams of P4O6. So 5.5 divided by the molar mass of P4O6, which is 220, is gonna give us an answer of 0.025. Okay? Now, it reacts with 20 grams of O2, so 20 divided by 32. If you put it on the calculator, you are gonna get 0.625. Now, to find out which one is the limiting reagent, we are gonna divide by their coefficient. So divided by 1 divided by 2. This stays 0.025. This one, however, becomes 0.3125. So this is definitely smaller. That means our limiting reagent is gonna be P4O6. Now they need what mass of P4O10 is produced. Since P4O6 is our limiting reagent, it is the thing we are gonna be focusing on, or it is our basis. So that means the number of moles of P4O6 is what is gonna affect the number of moles of P4O10. So we said it is 5.5 divided by 220, which is 0.025. So if 1 will give us 0.025 moles, then again 1 mole of P4O10 is gonna give us 0.025 moles. So they need what? They need the mass, so it is gonna be 0.025 multiplied by the molar mass, which is 284. So if you do it on the calculator, 284, you are gonna get an answer of 7.1, but they needed three significant figures, so 7.10. So our answer over here is 7.10. Let us submit and hopefully we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.